Hey guys, welcome back for AP Chemistry. Today we're in Unit 13 and we're going to look at calculations in thermodynamics. You're listening to podcast 13.2 with me, Miss Gray. Good to see you again. Let's start by calculating entropy, delta S. We described entropy before to say if a system is more disordered or less disordered, but now when we calculate it, we're going to get a quantitative measurement, an exact number, because that's what scientists do. We measure stuff. Quantitative, I gotta spell here. Gotta concentrate. Quantitative measurement of the disorder of a system. So its symbol is delta S. And as you know from before, the delta means change, right? And generally speaking, we always take the final minus the initial when we're talking about delta something. The units for entropy are measured in joules per Kelvin, or if you're dealing with moles of substances, it's joules per Kelvin per mole, or kmol, or you'll see moles Kelvin. The way College Board likes to write this on your test is going to be like this: joules times kelvins to the -1 and moles to the -1. So you'll recognize those. It won't throw you for a loop because it all means the same thing. Standard entropy is signified by the delta S with a little circle here, like a degree sign. Standard entropy means we're measuring the entropy change at standard conditions for thermodynamics, which is 25 degrees Celsius, and a pressure of 1 atmosphere, or in metrics, 101.3 kPas, kilopascals. We also have to define what 0 means. So in our measuring scale, 0 would be a perfect crystal. So some ionic substance with every atom in exactly the right place in the crystal that's at 0 kelvins. So the atoms are locked into position and they're not moving all around. Then we would call that an entropy change of exactly 0 because there's no motion and everything's perfectly organized. Does such a crystal exist? Of course not. We just pretend like it does. So to calculate the entropy change, we would take the sum of the entropy of the products minus the sum of the entropy for the reactants. And of course, this goofy symbol here is meant to be the Greek letter sigma. Sigma is something used to represent the sum of things, right? Because we ran out of S's in the American letters, we had to borrow Greek letters. So that's what that sigma is for. This should look familiar to you. It looks a lot like calculating the enthalpy change. Remember calculating delta H using Hess's law? It's a similar process. It's the products minus the reactants to calculate the enthalpy change for any given reaction. We're going to do something really similar here. Just pay attention to your units. So here's an example. We're going to use the Appendix C in your book, Appendix C. Sorry, I didn't tell you which one it is. It's on page 558 in the Brown-LeMay 10th edition AP Chemistry book. So if you're using a different chemistry book, find the one that has the table of values for delta H and delta G and delta S. So look for that appendix in your book, find a table like that, and we're going to work out these problems. So first of all, I'm just going to look up the values for my balanced equation. So for hydrogen gas, delta S is 130.6 joules per Kelvin mole, joules per kmol. And then chlorine gas, make sure you pay attention to phase, is 223.0 joules per kmol. And hydrogen chloride is 186.7 joules per kmol. Remember, when HCl is in a gas form, it's not hydrochloric acid, not until it dissolves in water. So we call it hydrogen chloride. So watch the phases and make sure you get the right values from your book. Now we're going to use the delta S equation. So we take the sum of the products. I have 2 HCl's, so 2 times 186.7, and I subtract from that the sum of my reactants. So I have only one hydrogen gas, 130.6, and I have one chlorine gas, 223.0. I find the sum of those, apply my calculator, so let's go ahead and do that. Gotta unlock my calculator. All right, so let's type it in. 2 times 186.7 minus the sum of 130.6 plus 223. Great, so it is 19.8 joules per Kelvin per mole. 19.8 joules K to the minus 1, mole to the minus 1. That's it. That's all we have to do when we are provided with a table of values like that. And of course there's other ways. They might ask the question, and I'm going to show you other ways to find delta S later on. In example 3, it asks us to calculate delta S for both the forward and reverse reactions for the synthesis of water. So the assumption here is that you know what this word means. Synthesis means creating water, so water is a product in the forward reaction. And what does water come from? Synthesis means we put together hydrogen gas and oxygen gas. Let me label these. And we made water. Most people think of water in its liquid phase, and so that's the number I have on my paper. That's the number we're going to do. If you put water vapor, that's perfectly okay, but then you'll be looking for another number in your table besides the one I have here. Now, before we can approach this problem, we have to start with a balanced equation, and this one is not balanced yet. So let me just take care of that. I need 2 waters here and 2 hydrogen molecules there. Now I've got my forward reaction all written out. And I'm going to put my numbers in. The hydrogen is still 130.6. Oxygen is 205. And then water is 69.91. These values are all in units of joules per Kelvin per mole from the table in your book. So now let's calculate delta S for the forward reaction. So I take my products, 2 waters, minus my reactants. So I have to add up 2 hydrogen gases and 1 oxygen. All right, time for a calculator. Oh, trying to mess up already. So 2 times 69.91 minus the sum of 2 hydrogen gases and 1 water. Okay, so we got negative 326.38 joules per kmol. And of course we would evaluate sig figs. Looks like I get to keep 3 of them, so negative 326. What do you suppose the entropy change for the reverse reaction is going to be now? You may already have an idea of what it should be. Based on what you know about enthalpy change, if you reverse the reaction, what do we do with the heat? Do you remember? Well, let's see if it works here. So I'm going to write the reaction backwards. So here's my reverse reaction. 2 liquid waters would split apart into 2 hydrogen gas molecules and 1 oxygen gas molecule. So now, to calculate delta S for the reverse reaction, I take the sum of my products, which was 2 hydrogens and 1 oxygen, and I subtract the sum of my reactants, 2 liquid waters, 2 times 69.91, and then we'll put this through our calculator just to see if our suspicion is correct. I haven't told you the right answer because I want you to see for yourself. So I take 2 times 130.6 plus 205, and I'm going to subtract from that answer 2 liquid waters. Hey, it's the same number, only the sign is switched. So it's just like in enthalpy. When we switch the reaction, we change the sign. So now it's a positive 326 joules per kmol. Is that what you thought all along? Aren't you clever? I had to work it out the first time, but now I know. The reverse reaction is going to have the opposite sign of the forward reaction. So if you have to add reactions together and you flip one around, don't forget to change the sign. So now let's take what we know about delta S and let's apply it to delta G. Gibbs free energy change is going to be represented with this symbol delta G. And this represents the maximum amount of energy that can be coupled to another process to do useful work. And in this class, the other process that we're talking about is chemical reactions. We're getting free energy from the energy stored in the bonds between molecules and atoms. So chemical reactions is our process that we are coupled with. Of course, the Gibbs free energy change is going to be related to entropy and enthalpy. Remember, total mechanical energy is going to be equal to heat plus work. And so this is the free energy that we're looking at, heat and how much is left to do work. I think we already saw that. There we go. Here's what I want to see. So to calculate Gibbs free energy, then we take the enthalpy change, delta H, minus the temperature times the entropy change, minus T delta S, where, here, let's label these, shall we? Delta G represents our Gibbs free energy change, so free energy, and we relate this, remember, to spontaneity. The spontaneity of our reaction. And then delta H is the enthalpy change. We have several ways to get to delta H. And then, of course, T is temperature in kelvins, not in Celsius or Fahrenheit. So T is Kelvin temperature. And then delta S is, of course, the entropy change that we just learned how to calculate. So if delta G is negative, then we consider the process to be spontaneous, because that would be a situation in which delta H is negative and delta S is positive. That would be a spontaneous process. Sorry, I don't want that box there anymore. I don't want the box. Go back. Okay, gonna have to live with the box. And then if delta G is positive, the process is non-spontaneous. Because in that case, delta H would be positive, or delta S would be so negative that it overrides the delta H. And then what if we have a delta G of 0? Then what? Then it's neither spontaneous or non-spontaneous? No forward, no reverse, then what? That just means that your process is at equilibrium, because then there's no more net change in the concentration of either reactants or products. So that's going to be useful when we're trying to solve equilibrium problems and we know what delta G is. We can use that to make some predictions. It's going to be really powerful for us in podcast 13.3. So here's another example of a reaction where we're going to use thermodynamic calculations. So we'll calculate the free energy for the reaction to see if it is spontaneous at 25 degrees Celsius. Remember, since delta G is equal to delta H minus T delta S, we need to know delta H and delta S. So we're going to look up the values for each substance in the back of your book in the appendix, and we'll find the numbers for each substance. Remember, the heat of formation for any element is 0, so that makes this part easy. And then carbon dioxide is a gas, so be careful to get the right phase. It's negative 393.5, and this is in kilojoules per mole for delta H. So I'm just going to switch that so that I'm working only in joules. When we start bringing in the gas law constant, you're going to want to have all your values in joules. So if I could give you any tip that will save your life on thermodynamics problems, it would be work everything out in joules. Everything in joules. And then if it asks for kilojoules, you may convert it to kilojoules. You must if they ask for it in kilojoules, but it will save your life if you just work out every problem in joules, and then you won't have any issues with your units agreeing or not. And so my delta S values for carbon, solid carbon, I'm going to use the one for, I think this is the one for graphite, not for diamond. You can verify that in your book. And then 214 with CO2, and that's in joules per Kelvin mole. So now I need to work out delta H. So just like we did before, the heat of a reaction is equal to the sum of the products. So negative 393.5. Wait, that's got to be times 10 to the 3. So I'm just going to 1, 2, 3. So there we go. 393,500 joules per mole. And then I subtract the sum of the reactants. So 0 plus 0. Hey, that part was easy, huh? Now let's do delta S. So the entropy change for this reaction is the sum of the products, 214 joules per kmol, kmol, minus the sum of the reactants. So I'm going to add 5.69 plus 205, and that's also in joules per kmol. So for enthalpy change, of course, I get negative 393,500. For my entropy change, I got, let's see, I wrote it down. Oh. 3. No? Yes. No. What is this nonsense? I gotta get my calculator out. Okay. So I need to have 214 minus the sum of 205 and 5.69. 3.31. Yeah, it was close. So 3.31, and that is joules per Kelvin mole. So now let's find delta G. Delta G is going to be enthalpy minus temperature times the entropy. So it is negative 393,500 minus temperature is 25 degrees Celsius. Let's change that to kelvins. Add 273. So it's 298 kelvins times my delta S, 3.31. And we add those. Oh no, we're just multiplying them together. So no need for square brackets. I'm just getting a little carried away. Don't worry about me. Time for a calculator. Let's check this answer. So I have negative 393,500 minus 298 times 3.31. So delta G is a negative 394,486. We're not going to get to keep all of those digits. So how many sig figs shall we keep? Looks like 3 is what I get to keep. So I'm going to write this in scientific notation anyway. 3.94 times 10 to the third. No, sixth. Yeah. No, 5. I can't count. It was 394,000, so yeah, 10 to the 5th joules per Kelvin's canceled. So joules per mole, which is equal to 394 kilojoules per mole. That's how we would approach the delta G, Gibbs free energy calculation. You could use the values in the back of your book and do delta G of the products minus the sum of the delta G for the reactants, and you will probably get a value that is very similar. It may be slightly off due to rounding errors in these experimental values. This table of values is derived from experiments done over and over, so it's not perfect. But usually in an AP chemistry problem, you're not going to be given a table in the back of your book. You'll be given data about entropy and enthalpy. So use delta H minus T delta S to calculate the delta G. Got it? Okay, that's it for podcast 13.2.